Will this be useful for non-uniform, non-rectangular grids?
No, I need somebody to generalize this to non-rectangular grid, but structured grid should be easy. But unstructured grid might have to take some work. Okay, you know the difference between structured grid and
No, I know what you're talking about.
structured grids are grids that are mapping of the rectilinear grid. Okay, so we have all the machinery that we need to write Maxwell's equations in the discrete world. Because we have all the operators that we need. But before we do that, let's try to get some insight as to what this divergence means. This divergence, as you see, you associate a 4 vector with the mn point that is over here and over here. Okay? And the discrete divergence is essentially take the back vector, which is take the value at this point and that point over there, and make a difference. Okay? And then for this other thing, it also makes a difference. So the discrete divergence is essentially finding the flux that leaves and enter this box. Okay, because you take the value that is at this point and did the backward difference, so you find the flux that's entering this box from this direction, and then the other component you're just finding the flux that's entering this box in this direction. So it's quite clear that Gauss theorem holds. Discrete Gauss theorem. So if we have many of these vector fields on the rectilinear grid, say in 2 dimensions, say if we draw things in 2 dimensions, and then for every point there is a 4 vector associated with that point in 2 dimensions. And it's quite clear that if you take a discrete divergence about any point, it's actually taking this flux, and that flux, and subtracting and adding them to see the total flux passing through this box. Okay? So it's quite clear that Gauss theorem holds in the sense that if I would add up these divergences about all these points up, if I were to add them all up, all the interior fluxes cancel each other. And what I'm left with is just a surface flux. Okay, I can draw this even bigger picture if you want to. Okay, if I take all these divergences and add them up together, the interior fluxes will cancel, leaving behind a surface flux. So I can write the discrete Gauss theorem that if I have the discrete divergence of this 4 vector, and this means just the x, the y, okay, delta x, delta y. Okay, in these 2 dimensions, just delta x, delta y. If I were to sum up all these discrete divergences according to these boxes, okay, according to this summation, according to a volume that I define, it will be equal to the same sum of these vectors on the surfaces. Okay, on the surfaces. So there's some kind of a discrete Gauss theorem here too that you can impose, that you can arrive at. And similarly, if you look at the Stokes theorem, whether it holds true in the discrete world, the Stokes theorem, in the 2D case, I was saying that the discrete curl is just actually adding up the circulation of this thing. And if I will have the circulation of this defined at this point plus the circulation of that defined at point, all the interior circulation will cancel each other, and then you get discrete Stokes theorem. In 2D, it's quite easy to see. And it also happens in 3D. If you were to integrate over a contorted surface on this discrete wall, all the interior circulations will cancel each other, leaving only circulations on the boundary of that composite surface. So you can see quite easily that there is also discrete Stokes theorem. Okay, which means that if you take all the interior circulations in the discretized ball and sum them up, okay, according to this thing, it will be just equal to the circulation of this near the edge. Some contour. So the discrete Stokes theorem holds true depending on describe this as according to the surfaces in the discretized wall, and then we see according to some contour that goes around all those things in the discretized wall. And then you can go on and on. You can have discrete Green's theorem because the chain rule holds. Okay, you can have discrete Huygens principle. You can prove Huygens principle. And then you can have even discrete reciprocity theorem and discrete energy conservation, and everything that holds true in the continuum wall holds true in this discrete wall. Okay? So you can write down Maxwell's equation too with discrete electromagnetic theory and see how it looks like. And we'll write that out for you. Okay, discrete EM theory in this notation of the discretized wall will look something like this. Then I define a for operator, which is the curl operator. Okay, like what I defined over there for curl. Okay, and that it operates on MNP. You use a vector M to denote MNP, and that it operates on the form vector at the time step of L minus half is equal to partial T, and this is the discretized time step operator times B of M plus half. And this produces, let me see what it produces. It produces a back vector. Okay? We say that the curl operator produces a back vector. So this should be equal to that. Okay? And that I can write down the second Maxwell's equation in this discretized wall. And make sure that I don't write it down wrongly. It actually would have to use the back del operator operating on the magnetic fields, which are defined as back vectors at the minus half time step is equal to this derivative operator in the discretized wall L plus J of M L minus half. Okay? And M here just stands for M and P. Okay, M is a vector notation that stands for the grid point M and P. And let me define what the
so M vector minus half stands for M minus half, N minus half, and
yeah, M minus half for every component of them. Okay, M minus half is equal to M minus half, N minus half, P minus half. That's what I mean. Okay, so they are defined at the half grid point, and then the exponent, the superscript stands for the time location. Okay, because of this, this is the forward difference operator, this is a backward difference operator. Because this is the forward difference operator operating on this, give you something that is, did I have it right? Oh, okay, I have it wrong. It should be no L minus half. Okay, there's no L minus half there. So this is a forward difference in time. Okay. And you take this value at this time and then forward difference it and take it at a half grid point over. Okay, so this thing over here is L minus half, L minus 1. Okay, so this is L plus half. Since this is a forward difference operator, it takes a value here and the value here and approximate it with the time derivative. Okay, and then evaluate at the point L. So it's a central difference. It's second order accurate at this point L. Okay, even though this is a forward difference operator. Then this other one is the backward difference operator. It takes the value at L. Okay, do a backward difference L minus 1 and evaluate at L minus half. Okay, this is what this second equation means. Okay?
Excuse me?
Yes?
So write the current Jm is L minus half.
L minus half because it's outside this derivative. You can think of this to be on the same time step as the left hand side. Okay, it's over here. So this current should be at the L minus half time step, so that this equation becomes second order accurate in time derivative. Okay, so these equations are second order accurate, and you can actually write the other two Maxwell's equations in a similar fashion. That the divergence operator operating on the B field plus the half grid point as a back vector L minus half is equal to 0. Divergence of B is equal to rho n at L. Okay, you can also write down the other four Maxwell's equations in this manner. And then what is very important is that if you were to take the divergence of this equation, okay, but take the divergence of this equation, which you will take it with the fall operator, the back operator. If you were to take the divergence of this equation, this left hand side is equal to 0, right? Because it's back operator times back operator. And then you get this equation, okay, as this one over here. You get this equation as this one over here. Then you get the continuity equation, divergence of J plus partial T at rho is equal to 0. Okay, you get this equation. Yes?
Professor, in the Ampere's law over there, you're determining the H at the L minus 2 step by the D at the L step. Is this still causal? Do you have a issue with causality?
L minus half. Okay, these are Maxwell's equations written down, not assuming causality to begin with. We are just taking this derivative and assuming that we have the signal for all time, and we're just looking at one time to ask ourselves how the equation should look like. That's what Maxwell's equations in the continuum is like anyhow. Okay? So this will rely on time step before it comes about, right? This is a back difference. But you will have to rearrange this equation for time marching later on. You will put the future time quantity on the left-hand side and then past quantity on the right-hand side and do time marching with this equation. But at this point, we don't care. We just write down the derivatives without worrying about time marching. So you can use this for time marching if you rearrange the time dependence between those quantities and do time marching. But what is very important is that this equation actually satisfies charge continuity, which means that there's no production of spurious charges. That's why E algorithm is so stable. It does not have spurious solutions. It's stable at all frequencies and all time scales. It works at late time as well as early time. And if we apply it to solve for the cavity resonance solution, there's no spurious modes. Okay, because of this reason. All these equations are self-consistent. And all the four Maxwell's equations essentially retain the same form. In the discrete world, if you use the correct notation to write them. Okay? This is one important thing I'd like to emphasize. And of course, you can do this with time marching if you introduce the constitutive relationship that the magnetic field flux is equal to the magnetic field vector in this manner. You can use this constitutive relationship and then plug into that equation over there, and dm plus half, which is what we have with dm. Yeah, dm, not plus half, dm is epsilon m en. And then after you have this relationship, you can plug into these four Maxwell's equations and do time marching. You can put future quantities on the left-hand side, past quantities on the right-hand side, and do time marching. But what is wonderful about this is that charge is conserved. And you can also derive the discretized vector wave equation you derive the discretized vector wave equation by just taking the mu inverse and then the curl of this equation. Okay, you can show this equation quite easily. And this is the equation you have seen in chapter 1 of my book. Okay. Plus the two-time derivative, the forward difference, and the backward difference. Is equal to partial t tilde Jm L minus half. Okay? L minus half. You can get this very easily just by going through the discrete calculus. What is that?
How does that work? You have a backward difference and a forward difference in the same.
These two commute. You can operate on this first and then operate on that. It doesn't matter. In the beginning of this lecture, I showed that this. You can show that they commute. Okay, you can actually try them out for yourself. Just have this operating on f of L. You can show that the order doesn't matter. Okay. And what is more wonderful is that you can derive vector wave equation in this manner. You can also assume time harmonic signals. assuming that your signal is of a certain form, like for instance EML is of the form of EM e to the minus I omega L delta t. Essentially assuming a time harmonic form for your electromagnetic field, plug them into here, and all this discrete derivative will become simplified. Okay, they become simplified in the sense that you will have things like partial t hat or partial tilde will be 1 over delta t e to the minus I omega delta t minus 1. Okay, you want to see how this comes about? I can go to more detail to show you how this comes about if you want to. You want me to show you how this comes about? Okay, so we can show this in this very simple example. Dt f of L, assuming that if f of L is something like f of 0 e to the say minus I omega L delta t. So it has a very simple time dependence in this manner. Then by definition, this is equal to 1 over delta t f of L plus 1 minus f of L. Okay, and if you plug in f of L plus 1 into here, you get 1 over delta t f of 0 e to the minus I omega L plus 1 delta t minus f of 0 e to the minus I omega L delta t. Right? And then you take out the common term to both of them, which is f0 e to the minus I omega L delta t over delta t, which is times e to the minus I omega delta t minus 1. Okay. So what it means is that this derivative can be replaced with this quantity. So this is just f of L. So this whole derivative replace partial t of tilde. Okay, that. So which means that partial t of tilde can be replaced by that in the discrete pi as well. Okay. Of course, this becomes like in the limit when delta t goes to 0, this becomes I omega. This will become I omega when delta t tends to 0. If you look at this quantity, this cancels each other and becomes I omega when delta t goes to 0. You have a question?
I was going to say that form looks familiar when you have e to the I omega delta t minus 1. A lot of times in signal processing, you like to factor out e to the minus I omega delta t over 2 and then turn into a cosine. Is there like a, is there some intuition behind that?
It's a sinc function, right? Very often it's written up as a sinc function. Sinc function. Why do we have a sinc function?
Because now time
What is that?
At time delta t goes to 0, the sinc function becomes
1, right?
whatever, not 1, whatever is multiplying the argument. You have an I omega, you have an omega scaling, so
Right.
yeah.
It becomes a sinc function, but I think what Mike Wei wants to know, what is the physical meaning of this sinc function? Because you have some
broadening it in time, like now you have a discretized time, so the box, like instead of a delta function,
okay.
like which would be, or you'd be broadening your delta function into a box, right?
Okay.
So it seems like you'd expand that in this,
Yeah.
the transform.
Yeah. Yeah. Yeah, maybe something like that. I don't know. The derivative becomes something like that. It becomes like a sinc function. Kurt is trying to say that maybe this is because of the broadening of the delta function into a box. That's why I have sinc function. maybe it's related to that, but you often see this happening. Okay, a sinc function creeping in, and whether it has some physical significance, you can think about it.
But I think it is caused by the grid size because it's caused by the factor L+1. So if grid size is very, very small, this kind of distortion by gridding should not happen.
Right, this what happens. When the grid size, the step size becomes 0, this becomes I omega. You can see that, right? This becomes a sinc function. Sinc function, and then it becomes just I omega. Yeah. So we get back the continuum answer. But this discretized world is interesting in the sense that you can see all these things happening. But what is more interesting is that you can write the time harmonic version of this equation very easily now. The time harmonic version of this equation is that if you look at the delta t hat, which is the back differencing, it will become 1 over delta t, 1 minus e to the I omega delta t. Okay, which also becomes a sinc function of some sort. Okay, so this can be written as minus I omega e to the minus I delta t is according to what I have in my paper. This can be written as I omega e to the plus I delta t, where omega squared is a sinc function. Okay, according to, I'm just regurgitating what I have in my paper, which is a sinc function square. And then delta t is just that trick that you usually use in signal processing to make things into a sinc function. Okay, and then what you have is this equation in the frequency domain. This equation in the frequency domain. And you can write that down as tau hat cross mu m plus half dot cross E m minus omega square epsilon m dot E sub m I omega j sub m here. So you have one equation that's independent of time. If you substitute in and do this algebra. And this is wonderful in the sense that I can tell my student that solve Maxwell's equation in the complicated geometry. How do you do that? Well, you have this equation, if you understand what it means. This is just a matrix times a vector. I can put all these indices in a vector into a very long vector. Okay, maybe I can put this as a very long vector x minus omega squared times another matrix b times another vector x. The same vector x is equal to I omega times another vector s. This is what Maxwell's equations is all about. If you know how to identify the, think of this as being a vector and stack them up into a vector. Think of this as an operator. Okay, it is an operator that when it operates on this vector gives you another vector. And think of this as another operator. Think of it as another source. This becomes a matrix algebraic equation. And everybody knows how to solve matrix algebra equation in the computer. MATLAB has programs to do that. And you program this in MATLAB and obtain solutions to complicated geometry. You can obtain that in the time domain. You do time stepping, you can obtain that in the frequency domain by doing the solution to this equation. This is equivalent to finite difference frequency domain method, or FDFD. And if you solve this equation, depending on which form you want to solve it, this is equal to FDPD. If you do time stepping with it, okay. But you can get all this from just discrete electromagnetic theory. And note that this is stable. This actually preserves all the theorems of electromagnetics, and later on I show that Poynting's theorem holds true. Reciprocity theorem holds true. Green's theorem, Huygens principle, everything holds true. Okay? So this is very nice. This is not true for finite element method. You might make approximations to Maxwell's equations and end up with a finite element approximation to Maxwell's equation, but you cannot claim all the claims that I make in this paper. All the theorems are still there, everything is still there. So then the question is, did God actually give us continuum form of Maxwell's equation and the discretized form of Maxwell's equation? Maybe the nature of form is actually this discretized form. And what we learn in textbook is an approximation of the discretized form. Right? Because all the theorems I have here hold true. Right? Yes?
You're talking about small scale, everything is discretized.
Well, maybe at the very, very tiny length scale, Maxwell's equation is actually occurring in nature as a discretized form, not a continuum form. So when we observe things in the macroscopic scale, we just use continuum to approximate Maxwell's equations.
So I have a question about time and space, because for space, we can say space should not be absolutely so continuous, because there's a limit for differential of particle size or something. But
Right.
for time, we have a duality similar to uncertainty, but usually we take the time as intensity, infinitesimally continuous. So, but for time, the time part of a continuous version, it should be true instead of approximation.
But nobody knows, right? Nobody knows whether if you keep breaking time into smaller and smaller time steps, that you can still break time into smaller and smaller time steps. Nobody knows. Nobody knows that if you break space into smaller and smaller pieces, that you can still break space into smaller and smaller pieces. Right? Nobody knows. What we have is our equations that we have derived, assuming that space is infinitely divisible. But then that may not be true. Right? That may not be true.
So we have quantized time, just like a drop, but tickle to pass by one particle away instead of flowing continuously. Is that right?
But in your world, you see that the particles are moving continuously. Maybe in actual fact, they're actually jumping to space in discrete time. You never know. Right? So you never know.
Excuse me?
Yes?
So for the implementation point of view, so do we usually solve this wave equation directly, or we solve a set of the Maxwell equation?
We should solve this equation directly.
Yeah.
Of course, this equation is nicer to solve because you can tell the student to go to the computer and solve it directly. If he knows how to convert this into a matrix, put this as a vector, and all the things we have in digital computers can only deal with equations of this form. But if I write down this equation, something like this should be a mu inverse here, sorry, right? Should be mu inverse. If I write down this equation and ask my students to go and solve them, they'll scratch their head for many hours, right? Before they know how to go to the computer and solve it. You have to scratch your head for many hours before you figure out how to solve that equation on the computer. But if I give you this form, you just have to learn discrete calculus and then figure out how to write this equation in a computer form, and then go to the computer and solve it. Then I have a couple of students who have successfully started with these equations, went to the computer and solved problems that never had been solved before. But some of the waveguide problems, if you use finite element to do, they're almost impossible to do. But then when they use discrete calculus, discrete electromagnetic theory, they can go to the computer and get the matrix equation to solve very quickly. And there's no low frequency breakdown. There's no spurious modes, because charge is conserved. Okay? Charge is conserved. There's no occurrence of spurious modes. So this is one of the quickest way to get numerical solutions. Except that I have written this only for Cartesian grids. You can also write it for non-Cartesian grids because you can show that this grid in the electromagnetic theory maps to this grid. This is non-Cartesian. They map to each other very easily. These are called structural grids. Okay, but then more difficultly is that what happens if the grids are like this? They are not structural. I don't know how to draw them, but very complicated. But it's not the mapping of this thing into that grid. And how do I write down these equations? I do not know how to do that at this point. Maybe there is a form of this equation for unstructured grids. Then you can actually have a nice way of solving Maxwell's equations in a way that is very stable, no spurious modes, no solutions, and then all the conservation laws are preserved. Reciprocity theorems, Green's theorem, Huygens principle, all the theorems are preserved in this discretized form for a general grid. Then I do not know how to do it. Maybe someday some students of mine will figure out how to do it. Okay. One of the things that I want you to take note of is something called differential forms. Differential forms are another way of looking at electromagnetic theory from differential geometry. Okay, differential geometry. I can show that Maxwell's equations is intimately related to differential geometry. Then in differential forms, then there are the zero forms. Zero forms are